Good afternoon, sir.
Yeah, good afternoon.
Sir, let us start the
Yeah,
session.
madam.
Okay. Good
Yeah,
afternoon, one and all. I am S. Ruxana, Assistant Professor, Department of CSE. I welcome you all for the fifth day session of 1 week online faculty development program on role of big data and cloud in the era of transformation. A warm welcome to today's resource person, Dr. J. Pavan Kumar, sir. Thank you for accepting our invitation, sir. Now I request Jessica to introduce today's resource person.
We are honored to have Dr. Jekkipalli Pavan Kumar sir with us today to share their insights and experiences with us. Dr. Jekkipalli Pavan Kumar sir is highly accomplished individual in the field of graph theory and algorithms computer networks. Sir did his PhD in NIT Warangal in the year 2020 and he completed his bachelor's and master's in the University of JNTU Hyderabad. He worked as assistant professor in Mathrusri Engineering College, Hyderabad, ICFI, Hyderabad, Kakatiya Institute of Technology, Warangal, and Mallareddy Engineering College, Secunderabad. He also worked as research scholar in NIT Warangal from 2015 to 2020. Present, he is working at National Institute of Technology, Tiruchirappalli. Sir has participated in many workshops at national level, like recent trends in Domination in Graphs Master Training Program by NASSCOM. He also organized workshops like CRTCS and Blockchain Architecture at national level as chairman. Sir has invited to deliver his talks on web technologies, programming foundational mathematics for ML at various organizations, and one of them is statistical techniques for data science in VIT Bhopal. Thank you, sir.
Pawan Kumar, sir, I request you to take over the session, sir.
Yeah. Thanks for the introduction. First of all, thanks for giving this opportunity from Mr. Inayatullah. I have got the contact. Can I share my screen? Yeah. Am I audible now? Shall I start?
Yes, sir.
Yeah. Welcome to the session. In this session, we will be seeing some introduction to. Yeah, I'm getting difference. Yes. Can you mute yourself? I'm getting disturbance.
Okay, sir.
Yeah, thank you. Thank you. Yeah. Uh, in this session, I will try to give some intuition behind the MapReduce paradigm. In one sentence, if I need to introduce this particular one, means it is one of the problem-solving technique. Like in general, you might have encounter in your experience that there are several problem solving techniques or algorithm design techniques like divide and conquer, greedy, dynamic programming, branch and bound, backtracking. These are several uh, problem solving techniques. By using these, we can approach several problems, and based upon the problem feasibility, we can give some efficient algorithms. This is what we have seen in our experience. Now, in this session, we will be seeing MapReduce. Why we need to go for new paradigm? Already we are having these all. So, what is the necessity of going to this particular one, and how it is evolved? All these things we will try to go through. Like we will try to get the intuition. It is not concrete class like where I will be delivering entire concept in detail, and it is not such kind of thing. So I'm making your expectations as minimal as possible. This is my request. From this session, what we can discuss is how this particular map reduce paradigm has been evolved. What is the necessity of this particular one? This intuition we will be getting, and one or two examples of this we will be seeing. This is what the overall, if possible, at the end I will try to show one research problem where we can use this map reduce paradigm. Yeah. So this is the overview. Now let us consider if someone is interactive, I will be more happy. Someone who don't what you call have the disturbance with the mic, they can switch on the mic, unmute the mic, and they can interact. Thank you. So let us consider.
Okay, so will be
Yeah.
interactive.
Sorry, I'm getting the disturbance. That's the problem.
Okay.
Maybe with fan, I think. Yeah. Actually, first of all, we will be seeing how this big data. What is this big data? These things we'll be seeing. Okay. Now, as all of you are having, all we are having some devices, like we are having a computer, either it is a desktop or laptop, whatever it may be, one computer we are having, and some devices, mobile devices we are having. So, in computer terminology, this is also a computational node. This is also a computational node. Likewise, everyone is having some computational node, like computer or desktop or mobile or some other gadget. Everyone, every device could able to compute something. Now, from where this particular big data word has and if I think this is the last day of FDP, so I need not to tell what's the definition of big data and all. You might be knowing several V's, you might have heard several V's about big data, like volume, velocity, variety, veracity. Some V's are there. Okay, earlier they used to have three V's, then they have extended to six. Now I think more than 10 V's are there. These are being evolved over a period of time. Now let us consider V for volume, then variety, then another V is for velocity. Let us we will try to justify these words. Like we are not going to say what is this volume, what is this variety, what is this velocity. These are all things you might be knowing, that I am assuming. But is this the definition? Is this a sufficient definition for the big data? Like if the data is having huge volume, can we consider it as big data? If the data consists of several varieties of data, then can we consider it as big data? If the data is being produced very quickly, is that big data? Means these are necessary conditions but not sufficient conditions. Like maybe theoretically you might be knowing necessary in order to prove something, what are required to be ensured. Suppose one statement is there, we wanted to prove this particular statement, then there will be some conditions which are needed to prove, which are needed to what you call ensure in order to claim this particular statement. In order to prove that particular statement, we need to ensure these conditions. Like I can relate with some problem. You might be knowing um, in graphs I can relate. Like you consider two graphs are isomorphic. G and H are isomorphic. For this, what are the conditions? Means two graphs need to have same vertices, same edges, same degree sequence. Like this, we will be having several conditions. But if both graphs are having these all properties, satisfies these all properties, can we claim these two are isomorphic? Means no. But if two graphs are not satisfying any of these conditions, can we claim these two are non-isomorphic? Means yes. Just as a I can summarize like for a statement to prove, we will be using sufficient conditions. For a statement to disprove, we can make use of necessary conditions. I hope the point is clear to you. There are two types of conditions: necessary conditions, sufficient conditions. Necessary conditions are used to disprove some statement. Sufficient conditions are used to prove the statement. Okay. Now the coming to our discussion, that is big data. Whenever the data is huge in volume, then can we claim it as big data? Means no. Whenever the data is having several variety of data we are having, then can we claim it as big data? No. If it is having velocity, can we claim it as big data? No. If data is having all these three, can we claim it as big data? Then also the answer is no. The reason here is these all are necessary kind of conditions. Okay, but these are not what you call sufficient conditions. So now, how we can work with this definition? Basically, as we have discussed, everyone is having some computer. Let us assume, and this computer will be having several memories. Let us assume RAM and hard disk we will be having in a computer, and some capacity of memory we will be having. That capacity. Suppose we are running some program which requires 4 GB of RAM, 4 GB of main memory, but we are having only 2 GB. Then we cannot able to run that particular application on the given system. It is quite natural to have 2 GB of RAM, and we wanted to run some application which requires 4 GB of RAM. So it is this particular system is not suitable to run that particular application. Fine. Then what can be the solution, immediate solution that we will be thinking? Since we wanted to run such kind of application, we wanted to improve or extend the RAM. So we will be increasing the RAM from 2 to 4. So we'll be having 4 GB of RAM, and we can run that application. After some days, there is a requirement that we require 5 GB of RAM to run our application. There is another application which we wanted to run, and it requires 5 GB of RAM. But we are having only 4 GB of RAM in our system. So what is the next possibility? One next solution for it is from 4 to 6 we can extend, or from 4 to 8 we can extend, so that we can run application which requires 5 GB of main memory. Fine. And this is one of the solutions. Fine. Now you consider we wanted to store some data, like we are having the hard disk which is of capacity 80 GB, and we are having the data as 40 GB, and we can use this particular hard disk to store our data, and we can use this RAM to run our application. Everything is fine. But Suppose our data has increased to 140 GB. From 40 GB, our data has increased to 140 GB. Then our hard disk is not sufficient to store that data. Then what is the again the solution, possible solution? We can extend our hard disk capacity from 80 to 160 GB. Usually, hard disks are available in these kind of sizes. That's why I'm assuming like this. So 80 to 160, and we can store these 140 GB of data, and we can run on this particular machine. Fine. After some time, after some weeks of time, this has been increased. This data has been increased by 40 GB. Then our application requires 8 GB of RAM and 180 GB of data to be utilized. So 180 GB, but the capacity of this one is 160 only, so we cannot accommodate it. This again, what will be the solution? We may get 200 GB or 250 GB capacity of hard disk. Then we can store 180 GB of data, and we can run our application. Fine. Now, after some weeks, the requirement has changed from 140 to 180. So obviously, after some weeks, there is more chance that the requirement will shift from 180 to 200, 230, 270, 300. Likewise, again it will increase. There is more probability. Okay. Similarly, here also the RAM requirement from 5 GB to 16 GB or 15 GB, it may increase. Then our solution is what? Extending the RAM, extending the hard disk capacity. Likewise, we are considering. So, after some time, this solution is not feasible. After some time, some days, we can realize that this particular solution is not feasible. So, what can be done? So, what we can do is, here we are having one system which is having some capacity. Let us assume the basic thing, that is 80 GB. Like this problem occurred in your lab itself. In your lab, some systems will be there where the capacity of hard disk is limited to 80 GB or 160 GB, and the capacity of RAM is 4 GB. And we wanted to run some applications which require more space and more space in terms of main memory and secondary memory as well. So this is the requirement. So no system is having more than 8 GB. Yeah, could you able to follow? Please. Hello.
Yes,
Yeah. Now we are having several systems of capacity 80 GB as secondary memory and 4 GB as main memory. Likewise, we are having several systems. But what is our requirement is we are having like 180 GB of data and 8 GB RAM capacity we require. Okay, these are the requirements for now. But every system is having only 80 GB and 4 GB of RAM. So no system can hold entire data. This is for sure. Now, what is the implication? Can we what you call take out all these systems for scrap and keep new systems which contains a 250 GB of hard disk and some 16 GB of RAM? If that is the solution, then up to what extent we can go in that direction, that is uncertain. Definitely that is not the good direction, that you can understand from our discussion, right? So now what is the other solution is, whatever the commodity systems that we are having, commodity machines that we are having here, these commodity machines we can connect in a network. Okay, these all we can connect in a network by using some topology, either star topology, bus topology, whatever it may be. Some by using some topology we can connect in a network. So it is a network now. These all are connected in a network. Fine. Now, can we store 180 GB of data now? Yes, obviously some distribution we can do, so that out of these 240 GB we can keep 180 GB of data. Fine. But how we can give instruction to this particular network. And you consider this is holding some 60 GB of data out of 80. Okay, this 60 from this 180. Likewise, every system is holding 60, 60, 60. Okay, now this particular system lost this link. Okay, that is this system is down, then nobody could able to access this 60 GB of data. Yes or no? Suppose due to some system failure or the network failure, this particular system is unavailable, then also we could not able to work on this data. Okay, these are the implications from what you call this approach. Like whenever we have commodity machines and we have connected in network and we wanted to use these machines as collectively, then this is the problem we can face. Then what else is the solution is, in order to maintain machines these all machines, what we will do is we will keep one software here. These all connected in a network, and we are keeping one software to maintain these all systems. Okay, what is that system? Like you consider general system we are having, that is hardware we are having. In order to communicate with the hardware, we will be having some software. Through this software only we will be instructing all the things. What you call this software is operating system. Similarly, here also we are having hardware, where this entire thing is hardware, and to work with this hardware, we will be making use of, or we need to make use of software. Okay, that software we call it as operating system. Okay, and what is the difference between this operating system and this operating system is, this operating system will work on the devices which are present locally, but this operating system will work on the devices which are connected in the network. That means this system may present in some location and this system may present in some other location, this system may present in some other location. So these all systems can spread over several locations, and these all working together based upon this particular operating system. So this operating system we call it as distributed operating system. I hope you are able to follow.
Yes, sir.
Yeah. So now these all systems we are having, to work with these operating systems, we will be using one operating system called distributed operating system. Okay. Now you consider, for general operating system, here you come back to this normal operating system. In order to work with this operating system, we need to make use, let us consider this operating system is Unix or Linux platform. Now, in order to work with this, we will make use of several commands like cat, ls, then grep. Likewise, some several commands we will be using in order to create a file and performing several operations related to this machine. Okay, similarly here also we will be having distributed operating system. So for this also we will be requiring some system calls. Would you able to relate? Here we will be having Unix commands in order to communicate with this system, because Unix is the operating system, standalone operating system, we can say specifically this is standalone operating system, whereas this one is a distributed operating system, so it will have its own system calls. So those system calls we need to learn in order to work with this operating system. Okay, and as you know, computer will understand binary language. So if you instruct in machine language, then it could able to perform. But who can able to give instructions in machine language? That's why we are having some intermediate one, that is system calls. Okay, by making use of system calls, we can give instruction to the operating system. Similarly, here also we will make use of some system calls. By using these system calls, we could able to interact with the operating system. In turn, this operating system could able to perform operations on this hardware. Now you consider we are having the what you call the requirement to communicate with the operating system using system calls. Like there are some technologies like OpenMPI, some programming methodology like OpenMPI, OpenMP and MPI. These are several distributed operating system languages. By using these system calls, we could able to communicate with this operating system. But learning these is very much difficult. In olden days, some 20 years back, even 15 years back also, we used to have, this is the only way to communicate with the distributed operating system, in turn which will what you call, communicate with commodity machines. This was the only way to communicate with the distributed operating system. But and you can note it, what you call, understand the difficulty which was there earlier by using one fact that there used to be around less than 20 programmers who could able to program by using this. This was the situation earlier, some 15-20 years back. Entire what you call, software community, there used to be less than 20 people who could able to program in these language. That was the situation. So by keeping all these things, what can be done? So obviously, are we going to use system calls always by in the case of this normal system? Means no. We are making use of some languages like C, C++, Java. Those languages we are using, but those languages are not known to the machine. So what we require is we make we are making use of one software called compiler, which could able to translate this into the system calls or the machine language. Similarly, here on top of distributed operating system, in order to work with us, what we require is the compiler. So compiler is again a software like operating system. Compiler is also a software. So this is a second software that we require in order to work with these systems. Okay, now I am trying to summarize once again. Somebody may lose the what you call link. Let us try to revise once again. We are having commodity machines where the capacity of memory is limited. So we have connected all these in the network. So to work on these all machines, we require an operating system which is distributed operating system. And to work with a distributed operating system, we require to program in either OpenMP or MPI. But it is difficult. That's why we require one compiler which will accept our high level languages. Then it will convert into system calls or the machine instructions, and distributed operating system could able to understand those machine instructions, machine level instructions, and it will help us. Now the question is, what is this compiler? What kind of compilers are available? And shall I ask one question? Now, in order to work with these commodity machines, how many softwares are required? Yeah, please answer. Yeah.
Sir, is it two software, sir?
Yes, yeah, exactly. Two softwares we require. One is this operating system, another one is this compiler. Two softwares are required. So we will give input to this compiler, then compiler will generate machine level instructions. This operating system will work on those, and we can make use of this commodity software. Now, what happened after this is, instead of having these two, that is a compiler and a distributed operating system as two different softwares. Only one software has been developed. That software name is Hadoop. That software name is Hadoop. Okay. Now the question is, now we can replace these two software with Hadoop. This is one of the softwares. There exist several other softwares like Hadoop. Just in our discussion, we are considering Hadoop as one of the softwares which replaces these two softwares, that is operating system and compiler. Yeah. Now you consider when we have to use Hadoop. This is the question. When we have to use Hadoop is whenever we want to make use of these all commodity machines. Okay. Can't we use a single system? Means that discussion we have made already. Can't we use single machine means there there is a requirement to have more memory or more main memory or more secondary memory or more computational power. All these things matters. So now what is meant by big data is if some data is not fitting to the commodity machine. Try to understand this definition carefully. It is not a textbook definition. It is with working experience we can understand. Okay, it is not framed by me also. It is from senior professors. Try to understand this. What you call what is the intuition behind this word called big data. Big data, of course, the volume will be more, variety of data will be there, all these things matters. But the thing is, whatever the commodity machine we have, that machine is not capable of holding the data. Then we need to depend on several commodity machines which are connected in a network under this. Yes, please respond. Am I audible? Yeah, the data which is distributed across be considered as distributed what you call big data or not. This is the question. Okay, try the question. Okay, try to understand this question. Okay, you think about this question. What you call several problems. This is, and on top of it, only one thing, only one software, that is Hadoop, instead of two softwares, that is distributed operating system and the compiler together we are having as Hadoop. We are replacing with Hadoop. Now, this is the scenario which we have seen so far. Now, we consider the data. Please answer some of the questions. Now let us consider we are having a Google Maps kind of application. Okay, Google Maps. So I am in Tiruchi, which is in Tamil Nadu. I want to go to Delhi. Okay, you use this what you call this paradigm, then how it will work? Let us consider we will be having several in India alone, several locations like Delhi is here and Tamil Nadu is here. Somewhere here will be there. Finally, this will be the path. Let us assume, and within this Andhra Pradesh, if I search for two locations, can we get the route or not? Two locations within this Andhra Pradesh from A to B. If I want to go, are we getting the route or not?
Yes, sir.
Yes. Similarly, within this also we can get. Within this also we can get. Within this also we can get. Now you consider we are in Andhra Pradesh itself. There will be several locations within one particular state. There will be several district headquarters you can consider, and within one district we can have several mandal headquarters. Within one mandal we can have several what you call. We can say villages and all. So within one village also so many locations may exist. So all these locations together, if you consider, this is a huge data, isn't it? Volume wise, it is huge. And it is intuitive that this particular data may not fit in one particular machine. Could you able to relate? For one particular state itself, we will be having so many locations and among these locations there will be so many statistics, how much time it will take, how much, what is the distance, what are the transport modes available, all these things matters. So for one particular state itself, one commodity machine is sufficient, but we cannot store entire India map in one commodity machine. So whatever the data we are considering, that data is, what's the answer? That data is big
Distributed.
data. Yeah, distributed. Definitely it has to be distributed. So this data has to be distributed over several commodity machines. Okay. Now you consider Tamil Nadu data is present in this, Andhra Pradesh data is present in this. Similarly, Maharashtra, Madhya Pradesh, likewise Delhi data is here. Now, it is clear that no, and if you want to find the distance from here to here, then you can find the path. What is the path from you can go, and you can sum up all these. Then you can find what you call two stations. This Dijkstra algorithm we will try to apply in this particular one. Okay, Dijkstra algorithm, and you assume there won't be any negative cycles or negative weight edges. So Dijkstra algorithm should work. Now, is that the case in our example? Here we are having the data which is distributed across multiple machines. Now, can we apply Dijkstra's algorithm on this? Yeah, yes or no? Can we apply Dijkstra's algorithm on this data to find the route from Tiruchi to Delhi? Now the Tiruchi, that is the Tamil Nadu data is in one machine, Delhi data is in another machine. If entire data is with the
Yes,
same
sir.
system,
We can use
then
that algorithm.
then we can use. If entire data is present, refer even after this session also, the Dijkstra algorithm requires entire data to be present in single machine. Then it is difficult to apply this Dijkstra's algorithm. So we cannot use whatever the existing algorithm we have for shortest path finding. Okay. So what is the conclusion out of this discussion? This kind of architecture or this kind of framework. Is it clear?
Yes, sir.
Yeah. What is the reason is? What is the reason? Since all those algorithms assume that the data is present in the same machine, so entire data is available with the algorithm, so that it can work. But in our context, as the data is huge in volume with respect to the commodity machines, so the data is distributed across multiple commodity machines. So we cannot apply conventional algorithms. Okay, so there is a need to have one new type of algorithm. Okay, new type of algorithm where we can use this distributed data. That means we will be giving some algorithm which can run on this particular data independently, and on this data independently, on this data independently. Like Tamil Nadu map is given to is present in one system. Okay, to this one we will give some algorithm. Okay, and we will give algorithm to another one which contains Andhra Pradesh map, and we will give algorithm to another machine which contains Telangana map, which contains Madhya Pradesh map. Likewise, we will be giving one program which will run on all these systems concurrently, all these machines independently and concurrently on all these machines. Now, on that question alone to this Tamil Nadu go, what is the path? Then what it will give? There is no Delhi location in Tamil Nadu, it will say. From Andhra Pradesh, what there are no locations called Tiruchi and Delhi. Both are not known to me. Next, what it will tell? Madhya Pradesh, no location, no, those two locations are not known to me. Likewise, it will say, and Delhi machine will tell, that is the machine which contains Delhi data will tell, I don't know about Tiruchi, I know only about Delhi. Likewise, these all will respond to our algorithm in different ways. Okay, now there is one requirement that whatever the algorithm, suppose if you apply this one directly, then these will be the complication. So there is a requirement to have another type of program where we will be applying that program independently on every machine. We will be running that program on every machine independently or concurrently without contacting with other machine. Try to understand. Without contacting with this, we will be executing that algorithm in this machine. Similarly, without contacting with any other commodity machine, we will be executing in this machine. So we will be having one algorithm which will be common for, we have to give one algorithm which will run for all the which will run on all the commodity machines. Okay, this is the thing, because the data is distributed over all these commodity machines, and these all will give some response. Then finally, by you we could able to what you call deduce something, and we could able to give the path from Tiruchi to Delhi. Okay, what is the path and what is the distance, how much time, all these things we could able to give by using these results. This is the requirement. For this particular one, we will make use of one paradigm. Okay, try to understand. There are, like earlier we have seen, two softwares are required. One is operating system, another one is compiler. Similarly, here also we require two programs, two algorithms are the programs. One program is to run on individual machine, individual commodity machine, and these all will produce one result. Then to consolidate, you can get intuition, or you can understand for some time. You can keep like to accumulate all these, we require one more program. Okay, let us consider this program, first program as A, second program as B. Okay, first we will run program A on these machines, then these will produce on another machine, and we will apply for that, we will apply another algorithm. Algorithms are two programs, one is A, another one is B. One is A, another one is B. What this A will do is, whatever the data which is present, how the data has to be, how the data is distributed, that is immaterial to it. What it will do is, on that particular data, whatever it is available, like Tamil Nadu data will be vast compared to Telangana data. Andhra Pradesh data is vast compared to Telangana data. Telangana data is what you call vast compared to Delhi data, right? But these all will produce some results. So on all these, this particular algorithm will be applied. A will be applied on all these data. Then it will produce several results. These results will be stored somewhere. Whenever it completes its execution, it will store. Likewise, these all will be stored. And there will be another program, as we have discussed, that is B. So this B will run on this these results, and it will produce some output. This will be the final output of the algorithm, which can be, in our example, the route from Tiruchi to Delhi. Okay, this is what the intuition, and let us name these as this algorithm A is nothing but a mapper, and algorithm B is nothing but a reducer. Algorithm A is nothing but mapper, algorithm B is nothing but reducer logic. Okay. Now let us see one simple example. Like you consider, um, we are having one big book called Ramayana. Okay, one book. You can assume any other big book. Just I am considering Ramayana, which contains so many pages. Okay, let us consider some 10,000 pages I am having. Okay, from this Ramayana book, what is my requirement is, what is my objective is, how many times the word Rama has repeated. This I want to find. Similarly, how many times the word called Sita has repeated. Likewise, I have some 10 words. Okay, for all those 10 words, I want to find how many times that particular word has repeated. Okay, likewise, this is the problem statement. So whatever the data which is present, that is 10,000 pages. Okay, let us assume one cannot find this particular count in less period. Like you consider, I have given these 10,000 pages to one student and asked him to count all these word frequency. Then he will say, I require some 3 months time to complete its task, this particular task. For each month, I will go through with around 3,000 pages. That means every day I will go with some how many, maybe 100 pages. Likewise, he will tell some period. But what I will say is, no, no, this 3 months period is not feasible. I want to complete it by 5 days. Okay. Now try to understand one interesting point in this. 10,000 pages of book. Here I have written 1 lakh. Sorry. 10,000 pages of book is big data or not? Yeah. Can you answer? 10,000 pages of document only you consider whether it is big data or not.
Yes, sir, it's big data only.
Why 10,000? Did you see 10,000 pages of document which is not fitting in any what you call system, which consists of some minimal requirements like 40 GB of hard disk and 2 GB of RAM? Is that sufficient or not? 10,000 pages of text.
For that process, it takes a time, sir.
Okay, but we are not dealing with the process, right? We are dealing with what? Only the volume, isn't it?
Yes, sir.
Yeah, volume wise, you tell. Volume wise, is it big data?
No, sir.
No. So it is displays volume, variety, velocity, veracity, all those is big data. But 10,000, we are claiming it as big data, but it is not having volume. Understand?
Yes, sir.
Now the point here is, although it is not having volume, why we need to deal in this particular environment? This is the question. Or in other words, I can reframe the same question like, although it is not having huge volume of data, what is the requirement to claim it as big data? Why we need time? And I am saying that answer that it is the big data. Okay, why we need to claim it as big data is now Ramayana book is having 10,000 pages, although it is not having volume. It is there will be another book which will be coming, like you consider Quran, which will be coming after this Ramayana. Immediately I need to count words from Quran, I need to count words from Bible, I need to count words from some other what you call large book. Now what characteristic you are observing? Yes, now Ramayana has come, I need to complete its processing.
Data
Yeah.
or volume.
Volume definitely not, it is out of choice. Why? Because volume 10,000 pages or 20,000 pages also it can fit in one device. That may not be the problem mostly. But what is the other thing? Just and here now Ramayana has come, and this we have to count the word count, we have to find in this Ramayana. Immediately another one will come, that is Quran. Immediately another book will come, Mahabharata. Likewise we will be getting these data continuously. What is this, hmm this is nothing but,
Velocity.
yeah, this is velocity. So, what is the conclusion from this discussion is what we can reduce. Whatever the characteristics of big data we have seen so far, that is volume or velocity or variety, all these, all are not required. But at least one is there, means there is a need to consider that particular data as big data, and we need to go with some special treatment to that kind of data. That's for sure. Okay. Now come back to this example. Is the point clear to you?
Yeah, yes, sir.
Yeah. Now you consider 10,000 pages. I need to count these all. And one student told 3 months time is required. Then I told within 5 days you need to complete. Then what he will say? No, sir, I cannot do alone. So give me some other students also. So that in my team, so that I can try to complete. Okay. Okay. Take 5 students or 10 students, like that. I will say. So 5 students. For all these 5 students, like let us say it is one student, is another student, another student. Likewise, we are having 5 students. I have given. Now, what is their duty is they need to count all these. So, out of these 10,000 pages, some pages will be uh, given to this student, and some pages to this student, some pages to this. Likewise, all these pages are distributed to these 5 students. Then, what is their task? Their task is they have to go through those pages line by line, even word by word. Whenever they find any of these, then they need to increment corresponding count. That is what they do, isn't it? That's the logic. Yeah, since it is a simple problem, you can figure out Rama how many times, first time repeated, second time whenever he sees Rama, then he will increment this count to 2. Likewise, for Sita, he will maintain the count. For Hanuman also, he will maintain the count. Likewise, entire thing he will maintain. Similarly, he will also go through word by word these pages, word by word, and he will also maintain Rama how many times, Lakshmana how many times, Sita how many times. Likewise, he will also maintain, isn't it? Similarly, he will also maintain. Okay. Now you consider what is the process of getting this result. This is the question. What is the process? What he is doing? He is going through each and every page word by word. Whenever he finds any of these words, try to relate. Whenever he finds any of these words, he is making the count increment correspondingly, respectively. Okay, this is what the algorithm. What let us name these as ABCDE. These are the students. A is doing like that. What about B? What B has to do? A has to do like he has to go through line by line, word by word. Whenever he finds any of these words, correspondingly he has to increment the count. Now, what B has to do? Yes, please respond now. Sorry, Hmm.
Sir, B also does a similar work as A did, sir.
Yeah, similar work. What about C? C also similar, isn't it? D also same work. E also same work. That means whatever the process these all people are doing, that should be unique. That should be same. Okay? That particular logic we call it as mapper logic. Okay? Next, after this step, everyone will have, A will have the count for all these words. Rama 20 times, Sita some 10 times. Likewise, he will be having the list. Similarly, B will be having his own list, C will be having his own list, D will be having his own list. Likewise, we will have. Now, here we will be having some other students. Let us assume some other students. Okay, I am giving the names as F, G, H, I, J. Okay, now what K will do is K has to get these counts. Okay, these counts, and he has to count for Rama. That means whatever the list he received, from that Rama account he will get it. That is from here 20, here from here 25, from here 47. Likewise, some count will be there. All these counts will be given to this K. Next, this G, what G will do? He will collect all these and he will make a list for Sita. Next, H will collect all these and he will make a list. Similarly, I, J. Now, what these people have to do, K or G or H, K, sorry, this is F, right? This is F, G, H, I, J. These all five people, what has to do? Whatever the list they received, those numbers they have to add, isn't it? Here the list is there. These all list elements, these list count, they have to sum up so that they will get entire count in 10,000 pages of Ramayana. Yes or no?
Yes,
Yeah.
sir.
What is the logic here? Whatever the count they received, those counts they need to add. That's it. So is the logic common for common across these five people?
Yes, sir, it's common.
It is common. So that logic is called reducer logic. Okay. So after performing this reducer logic, after executing this reducer logic, we will be getting finally the result. Okay. This is overview of MapReduce. Let us give some. Let us go through some formal what you call things like what is the input for the mapper, what is the input for the reducer, what is the output of the mapper, what is the output of the reducer. These things we need to know. Okay. For all these four questions, the answer is same. That is for the mapper or reducer, input and output both are key value pairs. What is meant by key, what is meant by value? I think you know what is meant by key value pair. Suppose in your class there will be some students, okay, they will have some rule number and their details will be listed. So the rule number will be the key, the details will be the value. Likewise, the key value together, that pair we will be giving as the input for mapper as well as reducer. For mapper output also we will be getting key value pairs, reducer output also will be getting as key value pair. Okay, now pertaining to this particular example, what is the output of mapper? What kind of output we are getting from the mapper? Rama, then count. That means Rama is the key and what is the value? The count. Similarly, what is the input for reducer? Again same, isn't it? Input for the reducer. What is the input for output for the from the reducer? Rama, cumulative count. So key and the value. So key value pair is the count, what you call, is the input and output for mapper and reducer. Okay, next, in our discussion you might have got some doubt, or you should get some doubt. That is, 3 months time student has asked, then I told within 5 days you have to complete. For that I have given 4 more students including him. Now 5 students I have given, their names I have given as ABCDE. This is the story which we have framed so far. Now ABCDE are the students and they are finding the count for the designated pages. Rama how many count, Sita how many count, Hanuman how many count, all these things that they will be making. After that they will be giving individual counts to F, G, H, I, J. Who are these F, G, H, I, J? Who are these? These are different students, it seems, isn't it? But I have given only 5 sorry, 5 students, isn't it? Yes or no? Do you understand the question?
Yes, sir.
Yeah, I have given only 5 students A, B, C, D, E, but they have done their job, but our task is not yet completed. So in order to complete that, I am depending on F, G, H, I, J. Who are these? Again, 5 more students means whether these 5 will be available to me or not. Whether I have access to 10 students totally or not, I don't know. I may have access to only 8 or only 5. In that case, what can be done? Who will do this task? Is for that purpose only. There is this is interesting. Try to get the intuition. Okay, not what's called exactly how we will be doing and all. You can learn within half day. But getting the intuition is very very important, which will be useful while solving the problem. Like you consider, A has counted quickly. A has counted quickly and B is taking little more time. C is taking even more time. D is completing in decent time. E is also completing in decent time. About assumption, okay, assumption about their capabilities like that. Let us assume. So out of A, B, C, D, E, who will complete first?
Yes, sir.
Yeah, A will complete first it. So after completing it, that node A is nothing but one student, right? One student could able to perform something. Okay, he will be free. He will be free. Then what he can do is, instead of waiting for B, C, D, E to complete their task, what he can do is he can submit his result, whatever he has done, whatever the job he has to do, that job he can complete. Afterwards, he can uh, he can act as the reducer. Then this F is nothing but A. Understand? After completing that job, this result can be given and A can act as the reducer. Then this reducer logic can be executed by A. Now the question is, A has produced some result, to whom he will give so that he can come as the reducer. At that time reducer was not ready. Why? Because A only the mapper and the reducer in this context. So reducer was not ready, and moreover these all A, B, C, D, E are executing still. So in order to address this kind of thing, there is some memory, okay, some mechanism in between where we can give the result of map stage to this particular component, and this commodity machine can be freed so that it can go and act as the reducer. Try to understand, whatever the result produced by mapper can be given to this particular module, and it can release, that means it can say that this commodity job has completed as mapper, so that it can go here and act as the reducer. Is the point clear to you?
Yes, sir.
Yeah. Likewise, suppose we are having only 8 students available. Out of those, 5 you can give as mapper. Remaining 3 you can keep as reducer for the time being. Afterwards, after completing, 2 more also can be added as the reducers. Or only 5 are available, then those 5 only can be considered as reducers. Or only 5 are available and only 2 reducers are sufficient for the given problem. Likewise, the conclusion here you need to understand, the point you need to get from this discussion is, same machine can execute both mapper and reducer. Okay. In other words, same machine can be a mapper and reducer. Okay, what is meant by mapper? This is the question again. What is meant by mapper is the machine which is executing mapper logic, that is nothing but mapper. The machine which is executing reducer logic, that is nothing but reducer. So in one machine itself, we can execute both mapper logic and reducer logic, not at a time, both at different times. That is possible. Is the discussion clear to you?
Yes, sir.
Yeah. Now, I will give you one, at this point, I will give you one real time in the sense, day-to-day life example. Suppose as a faculty, I am assuming you as faculty, I hope, you are conducting an exam for 600 students in a very big auditorium or one big examination hall. You are conducting for 600 students, and there will be like some what you call colleagues who will be invigilating, okay, along with you. So there are 4 invigilators or 6 invigilators. 600 students are there, 6 invigilators are there in one examination hall. Okay, what are the duties of exam, what you call invigilator? Are like they have to collect all the scripts, they have to keep all the scripts in order, apart from invigilation. Okay, apart from monitoring, these are the 2 things they need to do at the end. Okay, now first thing is they have to collect, second thing is they have to arrange in order. Okay, these are the 2 things. Now in one particular column there are 100 students. There are 100 students in one particular column. So 6 faculty are there. So one faculty has can keep like one faculty can take one row, another faculty by another faculty, another row by another faculty. Likewise, it can be distributed. But there can be one faculty like me who is very lazy, and he will be going very slowly, and he could able to take only 20 papers. Meanwhile, others can take all 100 papers which are assigned to them. Could you able to follow? 6 rows are there, 100, 100, 100. 6 faculty are there, but one faculty could able to take only 20 within 1 minute. But whereas other faculty could able to take all 100 within 1 minute. Okay, usually what will be the tendency, usual tendency of the faculty? Yeah, can anyone able to respond? If this is the scenario, then how other faculty will respond?
Other faculty will be wait.
Other faculty will wait. Yeah, any other answers? Of course, that is also feasible solution. Any other?
The faculties will help others, sir,
Yeah,
who can.
yeah. That means whoever completes, he can come and take in charge of other row as well, isn't it? Yes. Faculty
Yes,
can
sir.
come to another row and he can take these scripts. And finally, sorting. You consider, you might be knowing merge sort. I hope merge sort. Just we can divide, we can sort it, and we can merge it. That logic can be applied on these all, isn't it? 600 scripts we have to arrange one by one means it is very very difficult. But if you divide among these six faculty, like you take some papers, you take some papers, you take some papers, and you sort those all and come with a sorted list, so that we can merge all those in one go. We can arrange all the scripts, although we are having 600 scripts. Okay, could you able to relate? Now that
Yes, sir.
now that sorting also will take some time for the sorting, and one faculty can sort his assigned scripts within less time. Other faculty will take more time. Then he can take again their scripts and he can keep it in sorted order, so that task can be completed within less time with the available resources. With the available six faculty itself, the task can be completed in less time. This is what observation you have to make. In this one, first task you can consider as mapper, how we will be collecting. Then the same person is coming to arrange in sorted order, that is a reducer. Okay, and if one and there is no possibility that all 100 all people, all faculty can collect 100 only all the time. One faculty can collect 80, other faculty can collect 120, other faculty can collect 60, another faculty can collect 140. Likewise there can be different distribution of papers. Okay, now that paper, those papers you consider as data. Okay, that papers you consider as data. Now whatever the faculty we are having, those faculty we consider as nodes, computing nodes or commodity machines. Now the data can be distributed in such a way that one commodity machine can receive small amount of data, whereas other machine can receive large amount of data. Okay, it is immaterial to this mapper and reducer logic. It should be immaterial to, or it should be independent of a mapper and reducer logic. Or in other words, in other direction, mapper and reducer logic should be independent of independent of how the distribution of data is being done. Okay, that is very, very crucial in MapReduce paradigm. Whatever the logic we make, that should be like in our context only you consider. Simple example, so you can relate easily. 10,000 pages. For A, I am giving 4,000 pages. For B, I am giving 1,000. For C, I am giving 1,500. For D, I am giving 1,500. Likewise, for E, I am giving remaining 1,000 pages. So now, irrespective of the distribution of data, the logic, mapper logic should be same or not? Is same or not, at least in this context?
Same.
Same, sir.
Yeah, that is very, very important in this. So, like you consider, we are giving, yeah, you can consider one problem, like we are having two matrices, we wanted to perform matrix multiplication. Matrix multiplication means we know a row will be multiplied with column. So every time to get one element, we require one row and one column. And this particular data has, you consider these are very large matrices, so we cannot load all the matrices in one particular machine, so we'll go with distributed environment. Okay, then we will we can make use of MapReduce. So we have to get one particular element by multiplying one row with one column. So whatever the way the data is being distributed, whether two rows are given and four columns are given to one particular system, and four rows and two columns are given, five rows and 10 columns are given to C, whatever may be the scenario, we could able to come up with uniform logic for mapper. Okay, same logic has to be applied on all the data chunks. Okay, all the data chunks, and these will produce some key value pair as output, and these will be given to reducers. And for reducer also we will be giving same logic across reducers. Okay, across these all machines, same logic has to be given, and that will be processed, then it will produce key value pair as output. Is the discussion clear?
Yeah, sir, it's clear.
Yeah. So in one sense, I can summarize like one node will be having some data. With that some data, it can produce some knowledge. Try to understand. One node will be having some data. With that data, if you perform some processing, it can create some knowledge. Similarly, B will be having some data, and when we process it, when we apply mapper logic, then it will produce some knowledge. Okay, these all knowledge are local to this particular data, isn't it? Whatever the knowledge produced by A, that is local to this data. Similarly, produced by B, this is local to this. So these all are local knowledges. Okay, these local knowledge are given to reducers, where we will be executing reducer logic, we will be performing reducer logic, then it will produce some knowledge which is global to the data. That is a surprising result. Try to understand. We are getting the local knowledge, and we are giving to the reducers. By applying reducer logic, we are able to produce the global knowledge which is common for entire data, which is applicable for entire data. So although the data is distributed across commodity machines, whenever we write mapper reducer program, we could able to get the conclusions or knowledge for entire data. Okay, this is what the requirement or the objective of this mapper and reducer. And some of the constraints that we have discussed, same logic has to be there for mapper, same logic has to be there for reducer, all this. Now, just to go back to one step, that is, we are having Hadoop, and these are the commodity machines, and conventional algorithms are not working. So we need to come up with one type of program that is called mapper and reducer. MapReduce program we need to have. Okay. Now, how many machines are there? And in those machines, how the data has to be distributed? Those are things who will tell. Try to understand the question and answer. We will be having some data, okay, and we are having several machines. Okay, how this data has to be distributed, how many nodes are there, how these nodes have to be assigned roles, like some nodes may be mappers, some nodes may be reducers, some nodes may be mappers and reducers. All these things, who will tell? Yeah, that's the answer. Who will give MapReduce program? User has to give MapReduce program.
One node can act as master node, sir.
Yeah. Actually, there should be one understanding, that is, user has to give map reduce program, that is, which consists of map module, reduce module, except that user need not give anything. Okay, it is the responsibility of Hadoop, which will take care of all the mapper nodes, reducer nodes, or data distribution. Everything will be taken care by Hadoop. That is the beauty of Hadoop. That is the responsibility of Hadoop actually. But as a user, what you can tell, or what we can tell is, how many mapper nodes you can take, some suggestion we can give, whether it will consider same number of nodes as mapper or not, that is what you call up to Hadoop, whether it will follow our instruction. It is just a suggestion or a guideline kind of thing. Whether it will follow or not, that is immaterial, that is not known. Okay. From the outside we will be knowing that in the network some 60 systems are connected, so you consider some 40 systems are mapper and 20 systems as a reducer. Likewise, you can give approximate value, but it may use only 5 systems as mapper and 3 systems as reducer, depending upon the data and how the data will be distributed. Everything will be taken care by Hadoop. Only thing user has to provide mandatorily is mapper code, reducer code, which is common across all the machines. This is the requirement. Is the point clear?
Clear, sir.
Yeah. And earlier we have thought that if you keep some data 60 GB, one out of 180 GB, 60 here, 60 here, 60 here, if this particular system is down, and we cannot perform any conclusion. We cannot give any conclusion on entire data, so entire system will be paused. Yes or no? This we have discussed. This we addressed. How this is handled in Hadoop? This is the question. Did you get the problem here? If one system is down, we cannot get conclusion on entire data. So how we can get it? How we can address this issue is, in order to address this kind of thing, what Hadoop will do is, every data it will keep at least 3 copies. Every data it will keep at least 3 copies by default without saying. If you want to keep even more number of copies, then you can give 4 copies or 5 copies. If you want to give, then you can give. So it is the responsibility of Hadoop to keep 3 copies, and if one of the copy is not available, where it is other copy where it is available, it will be known to the Hadoop and it will take care automatically, so that the processing can be done and the conclusion on entire data can be given in the stipulated time. Is the point clear?
Yes, sir.
Yeah, even you can give 10 what you call mirror copies also, but by default it will create 3 copies. Afterwards you can give how many number you want, those many copies it can create mirror copies. Okay, this is about introduction to this map reduce thing. Of course, always one thing is what you call available, that is, I can say there are 2 things. When we have commodity machines which are connected, then distributed operating system is there. On top of it, you can write OpenMPI, OpenMP or OpenMPI programs, so that you can utilize all these commodity machines. Okay, this is open even now also. But instead of that, there is one software which is Hadoop. Okay, one such kind of software which combines all both, that is Hadoop, so that we can get the same kind of advantage without learning these machine level programming. That is the advantage of using this Hadoop. Is that clear? And By using this OpenMP MPI, user has to deal with the data, how the data distribution should be. That is one thing, data distribution, and those data chunks, how to deal, what kind of processing we need to do. Here, MapReduce thing we need not apply. We cannot apply also. Whereas in Hadoop, just user headache is framing that MapReduce logic, except that remaining all will be taken care by Hadoop. How the data will be distributed, which nodes are mapper, which nodes are reducers, all these things will be taken care by Hadoop itself. That is the advantage. Okay. Now, quickly I will revise these all things with formal slides. Even if you read also, you can understand whatever we have discussed. Those all are pointed here. MapReduce programming is one of the programming model, right, for data processing, and it is scalable and reliable. How it is reliable? How it is reliable? Yes, any answers? Just now we discussed one thing. Hadoop will keep how many copies, how many mirror copies? Yes?
3 copies, sir.
Yeah, 3 copies. So automatically if one goes, another one will be there. That will ensure reliability. Similarly, scalability in the sense, in OpenMPI programming, if you consider 5 systems are there with us, accordingly we will write the programming. Suppose 2 more systems added to our 5 systems, then we need to change entire programming. Or 2 systems are down, then we need to change entire programming. It is difficult to manage. Whereas in Hadoop, if 60 systems are there, 20 more systems are added. Just we can add without any what you call change in coding and all. Just mapper and reducer programming will be same. Those will be executed on any number of machines based upon the instruction given by the Hadoop. It will be taken care by Hadoop, so we need not worry what is the logic, how machines are being managed and all. So that is, this particular one will give the freedom to scale down the number of resources or scale up the number of resources. Similarly, the reliability is ensured. And this is also a divide and conquer. Why? Because the data is being divided into data chunks. How it will be divided, that will be taken care by Hadoop. Okay, it is also divide and conquer. And one more important point, wherever the data is there, there only the logic is going and we are executing. Okay, we are not sending the data across network. We are keeping the data somewhere, and at that particular station itself, we are executing the mapper logic. Okay, so the data movement is limited. Of course, some data movement will be there, but it is limited. Whereas in what you call original distributed environment, sorry, in distributed environment, we need to keep data movement, which will increase the bandwidth requirement. Okay, this is the challenge that we have addressed by using MapReduce, that we have overcome by using MapReduce paradigm. Yeah, that is what given here. And this parallelism you can consider. There are 2 types of parallelism as we have discussed. I will show you here. This is the task we need to perform: summation of x, summation of x square. Summation of x can be performed by in this machine. X square can be performed in this machine. So the data has to move here, has to move here. This is task parallelism. Whereas data parallelism means summation of x we have to perform on this particular data. Okay, data will for this particular data we will calculate here, for this particular data we will calculate here. We will not move data here and here, although we wanted to perform summation of, or you can consider summation of x square also we wanted to perform. Then summation of x and x square for this particular data chunk we will find out in this node. Likewise, we can get advantage of data parallelism. Okay, and coming to this MapReduce algorithms, one of the example is a sum of squares example. Here just 1, 2, 3, 4 are there. Sum of these squares we need to find out. Sum of x square, as earlier we have seen. One can go 1, 2, 3, 4 are divided like this. Okay, it need not divide like this. Okay, you consider 1 and 2 can be in first mapper, 3 and 4 can be in another mapper. Likewise, also it can be distributed, or 1, 2, 3 can be in one mapper, 4 can be in another mapper. But what is the logic? Mapper logic. Mapper logic should be same, right? Across devices, mapper logic should be same. What is that logic? Whatever the numbers we have, whatever the data we have, for all those data, we will find out the square and we will sum up. That is what we will do. So that mapper we will execute. Then those all will be given to the reducer, and in the reducer what we will do, just we will sum up these so that we will get. Okay, in this simple example it is just summing up. In some complex examples you can find little more work for reducer. Okay, and one more clarity also I need to do at this moment. Suppose we are having one task called T, okay, which is divided into first step, second step, third step, fourth step. Okay, after performing this first step, we have to perform this one, then this, then third one, then fourth one. Okay, now you can consider this one as the mapper. In mapper and reducer paradigm, where it will fit is this can be mapper, this can be reducer. What about these two? What about these two is, again, this will act as the mapper. This has to be considered as mapper. This has to be considered as the reducer. Like this, if a task is divided into 4 subtasks, then we can 4 subtasks which are independent. Then you can consider like MapReduce repeatedly. You may get doubt that suppose we are having a task which is divided into 3 subtasks. Then this will be mapper, this can be reducer. What about this one? What about this one is, even though we are having only one more subtask to be executed, we have to go with this cycle only, that is mapper and reducer. So this can be the mapper and the reducer logic will be empty. Or this can be the reducer, mapper logic can be empty. Likewise, you can make use of this MapReduce framework. Could you able to relate what I'm saying?
Yes, sir.
Yeah. That just I want to give one more clarity that all the problems we cannot solve in just 2 steps. That means mapper and reducer. Okay, so we may require 3 steps, then this is the scenario. We may require 4 steps, then this is the scenario. 5, likewise you can extend how many steps you want. So this is the intuition for discussing this. Yeah. Next, another similar example, sum of squares example itself, but sum of squares of even and odd numbers. You consider 1, 2, 3, 4. Out of these, mapper logic is same, just it needs to find the squares. But what it will give is, whether it is odd number or even number, it will find. Accordingly, it will frame key and value pair. Here, what is the output of mapper? Key and value. So, what is key? Odd. Odd is the key. What is the value? 1. Similarly, square of 2. What is the key? Even, and the value is 4. Similarly, square of 3. Odd is the key, 9 is the value. Likewise, key value pairs we have got as the output of the mapper. After that, these are given to reducer. And what is the reducer logic? Whatever it receives, like odd 1 comma 9, it has received these two, and this reducer receives even 4 comma 16. What is the reducer logic? Whatever the numbers it receives, those all numbers it has to sum up. That will be the reducer logic, which is common across these, so that we will get even comma 20, odd comma 10. Again, you can observe here, key value pair is the output. Okay, with another what's called relevant or similar example, sum of squares of odd, even, and prime. Now 1, 2, 3, 4, we the mapper logic is same. That is, we have to perform square, but key value pair, how we will frame? If it is odd comma 1. If it is even, we will keep even comma 4, and it is producing another key value pair, that is prime comma 4. Similarly, odd comma 9, prime comma 9. Next, square of 4, even comma 16. All these are given to three reducers. Even comma 4 and 16 will be received. Prime 4 and 9 will be received. Likewise, these all will be received by these reducers. So what is the task of reducer? Whatever the numbers it has received, those all it has to sum up. And what is the what you call result of the reducer? Again, key value pair. Yeah, could you able to relate? Yes.
Yes, sir.
Yeah. Now, this is a diagrammatic representation. In addition to mapper and reducer, which we have seen so far, there will be some optional fields like combine field will also be there, which is used to make the number of reducers less. Like if some task can be done here itself, at the mapper itself, then we need not go with reducer phase explicitly, so that reducer can I can relate like this. A task is divided into 1, 2, 3. Okay, 3 tasks, and one is mapper. And second one, in the second step, we are having very less work to do. Then, and this is independent of the results from others, so that these two can be combined. These two can be combined together and can be considered as the mapper logic itself. And this is the reducer. Likewise, you can use optional field, that is combine. Then partition is to decide how many reducers are required. Partition is to decide how many reducers are needed. Okay, and we have seen one thing called whenever mapper completes its execution, then it can go to mapper completes its execution, then it can store somewhere, and it can go and act as the reducer. This we have seen, right? So what is this one? This is nothing but shuffle and sort module. It can keep here, then it can go and act as the reducer. Okay. And this implementation wise, just a few details I will give. Like what is meant by mapper? Implementation wise, in Java, how we will implement is everything as a class. Mapper is a class. Okay, reducer is also a class. I think you might be knowing applet programming or servlet programming or thread programming. Anything is a class. Suppose one class is there, Java class. How you can make that class as a thread is by extending from thread class. If you remember, you can relate. If you know servlet programming, then how you can make one class as a servlet by extending from either a generic servlet or a HTTP servlet. Likewise, you might have explained in the class. So in order to make one class as a thread, we have to extend from thread class. Similarly, you have to, if you want to make one class as a servlet, you have to extend from generic servlet or HTTP servlet. If you want to make one class as mapper, then you have to extend from the class called mapper. you can observe in this. Just underlined one, you concentrate. We are defining a class called map for word count, okay, which is extending from mapper class. And here we are having this symbol. This will tell generic class. Generic class in the sense in C++ you might heard, or in general programming terminology, template classes you might be knowing, class templates. This is a kind of a class template. Here we can specify what are the types that we are going to use. Key value pair. What is the input for the mapper? Key value pair. What is the output for the mapper? Key value pair. So total input output both are key value pairs. While giving input, this is the key, this is the value. Try to understand. Four parameters are there, or four types are there. First type is key type, second one is value type. Similarly, for output also key value pair, output key is of type text, output is of type integer. Okay, you can understand from the mapper output, what we are getting, Rama comma 10. Rama is the text, 10 is the integer. Likewise, key value pair we are giving as the input and we are getting as the output, but key value types are different. Those types are mentioned here. This is first key type, this is first value type, this is output key type, this is output value type. Okay, now in the what you call, like we are having in servlets, or servlets you can consider, if you extend from generic servlet or HTTP servlet, you will be defining some methods, isn't it? In generic servlet you need to define a service method. Similarly, in mapper class also, whenever you extend from mapper, you need to define one function called map, okay, which is having the what you call prototype, or in Java terminology, what you call this, a signature. This one you need to define. So this is the logic which user has to define. Okay, remaining all are taken care by Hadoop. Only this mapper and reducer. Similarly, I hope this slide is giving some information to you who are new to this programming. Yes, we have to make mapper class by extending from mapper. Next, we have to implement what you call, give the definition for map function. These two are essential. Yeah. Next, similar, and this is already discussed. Next, you consider reducer. In this reducer also, again, one class we have to extend from reducer class, where again key value pair we have to provide. Those types we have to provide, and reduce function we have to define. So this is essential. If you provide these two, mapper logic and reducer logic, remaining will be taken care by Hadoop. And we can give, always we can suggest how many mapper nodes, how many reducer nodes, how we have to, some guidelines we can suggest, but there is no guarantee that it has to follow, it will follow in the same manner. Okay. Yeah, this is the concrete example you can observe. This is that this is entire data. This we have divided. You can observe from this symbol. This we have divided. From this mapper logic is just it will count these all words, and in the combine, here we are having this one twice, so we can combine it so that we can eliminate another time repetition. Then partition, how many reducer nodes we require, that can be known by using this one. And here we are having only one reducer here. So these all are combined here. Then we can get the final output as key value pair. This is the example for mapper and reducer. Yeah. These are the steps which we have followed in this. That is, those are described here. Yeah. With this, I am done from my side. If you have any if you want any clarifications, you can. I will try to address if I could. Yeah. Thank you.
Sir,
Yeah.
sir, are there any online platforms, sir, to practice this?
Online, actually, directly, it is not suggestible to go with online because even installation, especially with Hadoop, I am saying, even in installation and setup, in that also there will be so many points that we can experience, which will be helpful in troubleshooting and which will be helpful in figuring out how the architecture is, how it is being understanding. All these things can be cleared with more clarity. So I suggest you to make, if possible, in your institute, you can keep some 2, 3 systems or 5 systems if possible, and you can install Linux on all, even Ubuntu, and you can install Hadoop, and you can make the platform ready. Then you can practice MapReduce program. That is what I can suggest.
Okay, sir.
Yeah. If any doubts are there, I will answer. Otherwise, thank you. Okay. Partition in the sense, data partition, you mean? Data partition in general, it is meant in mapper phase, okay, not in reducer phase. Yeah, any other?
Okay, sir. I would like to express my sincere gratitude to you, sir, for an insightful session. Your expertise and engaging delivery have provided us and the participants with a deeper understanding of these technologies. Thank you so much, sir, for your valuable insights and for making this session an enriching experience. Thank you, sir.
Thank you very much. Thank you, Inayatullah, for inviting me. Thank you very much. Shall I leave?
Yes, sir, you can leave. Thank you,
Okay,
sir.
okay, thank you.
Thank you for all participants, and tomorrow's session will be tomorrow morning 10 o'clock. The feedback link will be posted in the YouTube chat. Kindly fill the form.